Chapter 12, slides 5 through 15. So now we're going to look at how we can make alcohols, where the alcohol functional group is in our product distribution. And you probably didn't recognize this, but we actually already know 7+ ways to make an alcohol functional group. So let's review a few of these. We can do an SN2 reaction, going all the way back to when we first learned this type of chemistry. We can react something like an alkyl halide with NaOH and perform an SN2. This got us to an alcohol, right? So that's plausible. All right, we also learned a couple methods with alkenes. I'll write them both here. We could do hydroboration. This is a SN4, right? And then after the workup with NaOH and HOOH and water, you end up with an OH on one side and an H on the other side, right? It's a hydration. It's a form of hydration. Hydroboration. We also saw alkenes getting 2 oxygens, 2 alcohols in a SN4 fashion. After workup, it ended up giving you a diol, a SN-diol, because of the mechanism. So that's another way we put 2 alcohols onto a carbon system, right? So those comprise 2 and 3. We have also looked at hydration from an alkene using pi-base chemistry, where you add a strong acid. It opens up in a Markovnikov direction, meaning it puts the carbocation at the more stable position and the hydrogen goes at the other side. And then if you were doing this in water, well, then your nucleophile would follow up in an SN1 fashion, right? Giving you, after all is said and done, ultimately, you would get to the alcohol at that more substituted position. The next few utilize the fact that you can start with an alkene and you can do something like MCPBA, which epoxidizes your alkene. And you can do SN1 chemistry, meaning you can add acid and say water or some other nucleophile. Doesn't really matter. And you're going to get the nucleophile on one side, opening it up to the alcohol on the other. Or you could have done it SN2 style, where you added a strong nucleophile and avoided the acid, in which case you would open up the alcohol to the other side. And in number 7, I remind you that an alkyne, if it's terminal, can be deprotonated with a base like NaNH2. You have a deprotonated alkyne. This is just a carbon nucleophile. And so you guys had the choice of doing, 1,2 additions or SN2 chemistry with it. Basically, it's just, yeah, I can take my carbon minus and I can do SN2-like chemistry on an epoxide. Opening the epoxide up and after workup giving me the alcohol. Or we could have introduced a carbonyl. And the carbon minus goes in and up, 1,2 addition. And after workup, you have an alcohol. All of these end with an alcohol functional group. Okay, and we're going to spend our time for the most part of these this section of slides on number 7. Okay, we're not going to be working with alkynes. We're going to actually learn a little bit more about carbon nucleophiles. We're going to expand our arsenal of carbon minuses that are afforded to us, although we're going to be using the same type of chemistry, so it won't really be drastically new. So let's think about this most common method, number 7, as it relates to forming alcohols as your product. Okay, so what I want to do is I want to remind you guys of the list of carbon minuses that we know to date, right? Remember, this is my little thing, right? A Nobel Prize, one of the Nobel Prize recipes equals new carbon-carbon bond formations. And what you'll notice is that for the most part, most of the reactions we cover in this class, whenever you see chemistry where, oh, you can make a carbon-carbon bond doing that chemistry, you'll see a name attributed to it. And more often than not, that name probably won a Nobel Prize. And so, like, I always joke that, you know, one of the recipes to winning a Nobel Prize is finding new ways of making carbon-carbon bonds. You heard it first here, ladies and gentlemen. Okay, so let's think about nucleophiles that are carbon minus. Okay, so this is my little aside here, just to remind us. We've done this exercise before. I want to do carbon electrophiles and carbon nucleophiles. Because again, to make a new carbon-carbon bond, one of the carbons has to be negative and one of them has to be positive, right? Or one's partially negative and one's full-on positive, or vice versa. So to date, we know a lot of carbon electrophiles, where the polarity of the carbon is more partial positive. We saw that whenever we attach a very electronegative halogen, that makes the carbon attached to the halogen due to the dipole electropositive. Okay. We also started working with epoxides, whereby each carbon attached to the oxygen is electrophilic. Some nucleophile will attack there, right? Because the carbon by the dipole and the strain of the ring makes that carbon susceptible to attack. And lastly, we saw that all manners of carbonyls, ketones, aldehydes, esters, all sorts, because of that strong dipole, double bonded to the oxygen, that carbon is susceptible to nucleophilic attack. All of those carbons highlighted in blue are partially positive. All right, so now carbon minus. How do we do that? Well, the only one we have right now is a deprotonated alkyne. So it's like you need the carbon minus, right? You need that carbon to be a terminal alkyne right now. That's all we got right now. So this slide introduces 2 new players to the carbon minus game. Okay, we're going to call it RLI, which really, if you look at it, is just carbon minus Li plus. Okay, it's an ionic bond. Fine, okay, that shouldn't be any surprise. And also we have RMGX. Okay, we'll talk a little bit more about this MGX in a minute. All right, so how do we make RLI, alkyl lithiums, or how do we make RMGX, Grignard reagents? Let's take a look first at the struggle to make carbon minus. The struggle is real. Let's start with ethane. Now, remember earlier, we talked about pKa. Straight up ethane has a pKa of what? I don't know, around 50 or 60. I mean, it is really difficult to deprotonate. Those hydrogens are on carbons. There's no polarity to them. If you take them off, the carbon minus left behind is not stable at all. So the pKa is rather high. They are not acidic protons. So trying to take something like sodium amide, right, and having it deprotonate is virtually impossible. And you can figure that out because if it were to happen, this minus would grab the hydrogen, right? Then you would actually make NH3. So the acid on the left is like 50 to 60, and the acid on the right, pKa of NH3 is like, I don't know, 35. There is a 15 to 20 pKa difference between these two. So is the arrow going to go towards the weaker acid? Well, it sure is, and it's not in this direction. It's largely, irreversibly in that direction. Means it stays at the starting materials. It means that base is not strong enough. Even though that's a really strong base, it's not even strong enough to deprotonate an alkane. So we can't do this. That's not how we make them. So we've got to explore different methods. One of the methods for doing it is to use magnesium metal. So what you do is you start with the alkyl halide of your choice. So let's say, you know, if ethane was what you wanted to be your nucleophile, then you start with ethyl bromide. And just like sodium, when we were doing sodium metal in that previous slide, magnesium metal can be cut. It's actually more stable. And so it's got 2 valence electrons. Okay, we are going to donate both valence electrons to the system. Okay, so these 2 electrons are getting donated to the carbon. The carbon is then going to accept the 2 electrons, right? So CH3, CH2, it's going to take those 2 electrons as a lone pair, but it already has 3 other bonds. So almost like an SN2, it's going to kick off the bromine. So bromine gets kicked off as Br minus. Carbon is now minus because it took the lone pair. So you have a -2 overall in your solution. The magnesium gave its 2 electrons away, so it's +2. So this whole thing is a neutral salt. And it's stabilized in the solvent system that it's placed in, which is an ether system. It's a polar aprotic system. We'll talk about why aprotic is important, but it needs to be polar because you need to stabilize this very unstable salt, right? It's a highly reactive molecule. That carbon minus is not happy. It is highly reactive. All right. So what's nice about this is that we can take these alkyl halides, and you can buy a variety of alkyl halides. You guys did SN1, SN2 lab last semester, and you guys worked with a large array of in-bottle commercially available alkyl halides. You can purchase a lot of them. You can purchase them with different halogens, iodine, bromine, chlorine, and you can also purchase them with different alkyl components to them. Just like SN2, iodine is better at making Grignards than bromine, which is better because it's following leaving group trends, right? Iodine's a better leaving group than bromine. So if you're trying to make a Grignard reagent and you're having trouble, try using a better leaving group. Switch to iodine if you were trying it with chlorine. So these salts, they come as a solution, right? So you're going to make it in solution. You're going to use it in the solution as a solution. You don't want to isolate it as a solid salt, solid precipitate because it's so reactive. You'd hopefully be working in a glove box or something because otherwise you'd have a problem. They're highly carbon minus reactive, but that's how you make it. You start with the alkyl halide of your choice and you add sodium metal. You buy these magnesium turnings and you let it stir in ether for a long time, kind of battering at the magnesium. Alternatively, you can make alkyl lithium. So again, you could have started with ethane or methane, right? It depends on what nucleophile. And just like the Grignards, you want to start with the alkyl halide. This has a very similar trend to what we saw with the sodium when we were trying to deprotonate alcohols. You need 2 equivalents of the lithium, okay? So how this happens is that you've got CH3 with the halogen. The first lithium, and again, we're talking about metal lithium here, so not as easy to make as the Grignards. You got to slice some highly reactive lithium metal, which wants to donate its 1 electron to the carbon, and when it receives that, it kicks out the bromine. So after the first equivalent, you're left with CH3 radical plus lithium got rid of its electron, so it's plus, and the bromine got kicked out as bromine minus. So you've just made your lithium bromide salt. The second equivalent of lithium with its outer electron gets donated, and you end with CH3. Now it has a lone pair, so it's negative. The lithium, the second equivalent of lithium, gave up its electron, so it's positive. Here is your methyl lithium. Okay, so you can generate those carbon minuses by starting with the alkyl halide and adding lithium metal. Now, both of these work. I'm not going to get into which one should you use. Either one is fine. Just consider them equivalent, right? Methyl lithium, methyl magnesium bromide, right? Whether you're using the Grignard or the organolithium, it really doesn't matter. They're great carbon minuses. At the end of the day, the lithium or the magnesium bromide, those are just counter ions. What's key here is the carbon nucleophile, right? So what can we do with these carbon nucleophiles? Well, we can do SN2, or because it's a strong carbon minus, or we can do 1,2 additions. So that's what we're going to focus on. Now the good news is, if you think about it, the SN2 additions on an alkyl halide don't work very well for these species. And that's a good thing. You know why? Because if that were the case, once you generated your final product here, wouldn't it just react with the starting material and do an SN2? Yeah, it would. So that's not what happens. We can very safely generate these methyl lithiums or alkyl lithiums and Grignard reagents because even though they are carbon minuses, they're actually poor SN2 nucleophiles. That would be a problem otherwise. Okay, so we're going to concentrate on the fact that we have 2 new carbon nucleophiles. That's the point here. Okay, 2 new carbon nucleophiles, and they're strong, right? Because they're large and in charge. They've got a carbon minus charge to them, so they're very unstable. So I want to point out that we are now formally introducing the new mechanism called 1,2 addition. And this is the schematic I have on your mechanistic motif handout. We're going to be concentrating on nucleophiles that are strong. So we only need our carbonyl to be partially positive. Okay, so we have our strong nucleophile and we have our partially positive carbon. The first step of a 1,2 addition, and it's called 1,2 addition the way that I've named it, is because you have 2 atoms, 1 and 2, and those are the only 2 atoms involved in this addition. So the nucleophile goes in, and the pi bond, which is the weakest bond, breaks, and those electrons go up into the oxygen. And thus you're forming a tetrahedral intermediate. It's an intermediate. It's very important to do that. There is an intermediate, it's tetrahedral in nature, and the oxygen in the intermediate has an O-. This has ramifications down the road as you study more chemistry, it's important to understand that it goes through this tetrahedral intermediate. Now, what you need to do next is to analyze all of the groups that are at the foot of this O-. You want to look at the R group. You want to evaluate what the heck you just put on, the nucleophile, and then the other group, Q. All right? Now, what we're going to notice is that sometimes R and Q, what you start with, those are the things that define the carbonyl as an aldehyde, a ketone, an ester. If, let's say, R and Q are a combination of carbons and or hydrogens, then those are not good leaving groups, right? Carbons and hydrogens are not good leaving groups. So you can't take them off. Carbons and hydrogens are not good leaving groups. So once they're there, they're not going to come off. So if the nucleophile, which I told you we're concentrating on our new nucleophile, if our new nucleophile is also a carbon, I'm putting another carbon on. Carbons are not good leaving groups. So therefore, everything I put on stays on. There's really nothing more to do with that O- than to just work it up and be done with it. So work it up under acidic conditions to put that proton back on, and you're done. And look, you've made an alcohol. So that's what we're going to focus on first. Let's use a Grignard and introduce an aldehyde. Let's walk through this mechanism. I have an electropositive carbon. I have, let's say I'm using ethyl magnesium bromide, right? I'll change it up. I'll use different Grignards just to give you an idea. Remember that it's the carbon that is negatively charged. It does have a hydrogen off of it, right? So there is a hydrogen here, right? And there is this, I know that we draw this bond, but really, it's really not, right? It's really just CH2 with a methyl. And the magnesium is 2+ and the bromine is 1-. So I just want you to be aware that very often people draw this bond here as if it's covalent. And so you have to get used to the fact that when you see it like that, it is an ionic system to be written out where the carbon really is like a carbon minus, right? It's more of that ionic nature. So you will see in, homework and in textbooks, you will see it with a bond, like a covalent bond. It takes a little getting used to. All right, now our minus carbon is attracted to the partially positive carbonyl. And let's just evaluate here. I've got a hydrogen on the left. I have, well, I'll make it methyl, make it something real. I have a carbon on the right, and I'm adding a carbon. So carbon minus comes in, and the pi bond breaks and goes up. This is the first step of my 1,2 addition, my in-up. Hydrogen to carbon to methyl to O-, and I've just added the red carbon with the CH3. Right, so this is CH2. So there you go. I've just made a new carbon-carbon bond. And then you can evaluate again. H, carbon, carbon. Those electrons are stuck up on the oxygen, and that's where they're going to stay until you work it up under acidic conditions so that the oxygen can get a proton back. The final product is, if you were just going to write it out, this 2-butanol. Again, we don't have to write in all the hydrogens and such, right? So it's okay to draw them out in that vicinity until you've finalized your product. Let's try a Grignard with a ketone. I'll make it a real ketone. I'll give you, let's do something like isopropyl magnesium chloride. I'm a big advocate of color coding. So there's my partially positive carbon. This carbon right here is full on negative. Okay, you can, again, you can get rid of that bond and say, well, this is just my counter ion. Chlorine minus, magnesium 2 plus, the whole, but that's just your counter ion here. So you don't have to pay too much attention to that guy. The carbon minus is what's going to attack in an in-up fashion. I've just added my red carbon. My carbon minus has made a bond to my partially positive carbon of the carbonyl. I then stop and evaluate. What do I have? Well, I have carbon, red carbon, carbon. Those aren't good leaving groups, right? Carbons and hydrogens are terrible leaving groups. So I'm stuck here. I work it up. Acidic conditions. My O minus grabs the proton, and I can make it look a little prettier. Count out your carbons. You can figure it all out from there and make it look a lot nicer. So there you go. Oh, look, I have a tertiary alcohol. Maybe I could do some SN1 chemistry with it. All right, let's do another one. Let's start with an acid halide and do methyl magnesium iodide. Let's break it down. Got a carbonyl here. The carbon is partially positive. The carbon of my Grignard is full on negative, right? Because the magnesium is 2 plus, the iodine is 1 minus, the whole thing is a salt. I can ignore the counter ion here and concentrate on my carbon minus, which goes in and up. Added the CH3 here. Here's my carbon minus. And now, here's where I've added something here. Ooh, substitution. What does that mean? Well, I have carbon, red carbon, and chlorine. Chlorine is neither a carbon or a hydrogen, and in fact, it is a good leaving group, right? So the O minus does not stay where it is. It will take its electrons, one of its lone pairs, and drop it back down because you've got a good leaving group. Now, of the two, like, do you want to stick with an O minus, or would you rather come down and out so that chlorine minus is now the negative charge? I mean, it's like you're substituting negative charges in a sense, right? I'm going to go in and up and substitute out. So this is the in and up. And this is down and out. So here's my CH3. Here's the carbon it made a bond with, and I kicked out chlorine minus, which is a terrible nucleophile because it's stable. It's a good leaving group. But guess what? I now have a ketone. And I just saw in the previous slide that ketones are reactive with Grignard reagents. So you know what? It keeps going. There's no way of stopping the train. Your methyl magnesium iodine can't help itself. It sees a ketone, so it keeps going. So you're probably going to want to add enough reagent to get all the way to the end, because you'll get this hot mess of a mixture if you don't assume that it's just going to go all the way. So this is your second addition, right? So we did in up, we did down out, and then we did a second in up. At this point, I have carbon, carbon, and carbon. None of them are good leaving groups, so the O- is stuck with the charge. I am now ready to work it up and call it a day. And there you go. There's your alcohol as your product. Now, two things here. I'm going to go back to this making alcohols slide. What you just saw was the down out step, getting you back to a carbonyl functional group. Then you have to evaluate, is the nucleophile reactive enough to do it again? Well, yeah, if it is, then it's going to do a second in up reaction followed by the workup. Now, I just showed you all of this in that last slide with the acid halide. What does that look like when we use our hands as models? All right, now we're going to do a Grignard on an ester. Let's say we started with this ethyl ester, and I'm going to react it with ethyl magnesium bromide. Again, I'm just throwing together an amalgam of different systems. We've got our carbon minus. Remember, it's not really attached to, right, the magnesium 2 plus, the bromine 1 minus. This is your counter ion. It's really the carbon minus we want to pay attention to because that is the unstable negative charge. The partially positive carbon is the carbonyl. And we're going to do our in, up. It's the first part of the 1,2 addition. In and up. And I just attached carbon, carbon. It's the carbon of the ethyl group attached to the electropositive carbon of the carbonyl. All right, now I have to evaluate. Remember, it's only carbons and hydrogens where I don't do down and out. I've got a carbon, I've got a red carbon. Ooh, I have an oxygen. Oxygen can be evacuated. Down and out. Where does that leave us? Leaves me with, right, carbon on the left, carbon on the right. I've got a ketone. I kind of shoved off this O minus with the ethyl. So the ethoxide group just kind of went away. All right, so I know that ketones are susceptible to reactions with Grignards. So it's going to keep going. It's going to do it again. In and up. O minus, original carbon. I've now added 2 of these red carbons. And if you take a look, I have carbon, carbon, carbon now flanking the blue carbon of my electrophile. And so I can't bring the electrons down. There's no good leaving group. Carbons are not good leaving groups. So I am done. I'm ready to work it up and protonate the O minus. and I end with an alcohol. Okay, very repetitive, makes sense. We know carbons and hydrogens are not good leaving groups, so we can follow this 1,2 addition / substitution regime in order to figure it out, no matter what the carbonyl given to us as my starting material is. All right, let's take a look at Grignards with an epoxide, because we know that electrophiles, we've got the carbonyls, but what about the epoxides? The good news here is that you guys already know this. We've looked at epoxides a lot when we were doing our alkene chemistry. So if I had an epoxide and I had a strong Grignard nucleophile, right, here's your counter ion. We're focusing on the strong carbon minus because that's the strong nucleophile. We have 2 carbons that are electrophilic, and when you're dealing with a strong nucleophile, you're thinking SN2. And so you've got a strong nucleophile, but the problem with epoxides is that you have 2 carbons that are electrophilic. But if you're under SN2 conditions, you want to avoid steric hindrance. So between carbons 1 and 2, we're going to attack carbon 1 from the back, opening it up. Giving us this system. We've just made a new carbon-carbon bond. And we've opened it up. You know what? You should actually still search for a down and out. See this O minus? Can it come down and out? Well, no. It's got carbon, hydrogen hidden, and the blue carbon. So nothing but carbons and hydrogens. It stays put until you work it up under acidic conditions. So the O minus gets protonated under acid-base acidic conditions. And we end with our final product. Wow. So we do know a lot of ways to make alcohols. The mechanisms are not bad. You just have to get into the rhythm of knowing what to do when you see a Grignard or an alkyl halide. An alkyl lithium. Now, I want you to understand that either one of these will work. RLI, if you go back to all of these, you could just say RLI. Same thing. For all of these, it could have been RLI. It doesn't matter how I give it to you. In any form, it is carbon minus. The lithium would be the counter ion. Since the Grignard was more new looking and more complex, I did those as the example. But every one of those mechanisms is the same, even if I'd given you methyl lithium or ethyl lithium. Now, a little bit of note about both of these reagents. Carbon minus is unstable. They are very, very strong nucleophiles. But remember, there's a fine line between nucleophiles and bases. So organolithium reagents and Grignard reagents are strong nucleophiles / bases. So if they're really strong bases, you can't run these reactions in any protic solvents. So you're never going to see a Grignard being run in water, right? As much as we'd love to use water as our universal solvent, since we can get it from the tap and it's green, we just can't use it. Otherwise, the Grignard's going to be so busy deprotonating the water, it's not going to attack our epoxide or attack our carbonyl. So do not use protic solvents like water or even ethanol. Just any protic solvent is a no-no when you're trying to use these carbon minus nucleophiles. They're too strong of a base. This goes for any protic system. You cannot, in your system, have any NHs around or SHs around or OHs around. Even terminal alkynes can be deprotonated using a carbon minus as a base. So if that's not what your intent is, then don't put those guys near a Grignard or an alkyl lithium. So here's some examples. If you had a starting material like this and you're like, oh yeah, I'm just trying to make my own Grignard over here where I add some magnesium metal to make the Grignard, yeah, that's not going to happen. Why? Because if you make the Grignard, you also have in your system a protic nitrogen. This is also, the second one is showing, oh yeah, you could make this into a Grignard. You could definitely make this Grignard. Totally doable. Here's the problem. Once you make this Grignard, another molecule of itself has a reactive species. So if you wanted to take this molecule and react it with the carbonyl of another molecule of itself, by all means. But if you wanted to introduce it to a different carbonyl and hope that it reacted over there, you might have some competition. So you just have to be aware that what you're making is reactive. So be careful. Don't give it any system that has an acidic proton in it. And don't have a bunch of ketones lying around that it can react with if you're like, no, I want it to react with the one I'm putting in. Well, it might not do that. Here are some examples for you to practice and try your hand at predicting the final products. Now you can assume all necessary workups for each and every reaction.